In the last video, we looked at calculating and interpreting a confidence interval for the mean. And this is a common statistical inference technique that we're going to use throughout the rest of the course. Another technique that we're going to use is that of hypothesis testing. And so what we're doing in this lesson is we're laying the foundations for the remainder of the course by covering these two ideas and trying to build up some intuition into how they work. So on the one hand, confidence intervals, and on the other hand, hypothesis testing. So in this video, we're going to look at hypothesis testing, and to do that, we're going to look at an example where some researchers were looking at toads and asking the question, do toads have a tendency towards right-handedness like humans do? So what they did was they collected 18 toads from the wild. They put a balloon over the toad's head and then observed which forelimb the toad used to remove the balloon. So hopefully no toads were harmed in this experiment. And what they found was that 14 of the toads tended to use their right forelimb predominantly to remove the balloon, whereas 4 of the toads used their left forelimb. And so they said, okay, 14 out of the 18 toads are right-handed and 4 out of the 18 are left-handed. Okay, so that's the experiment. The population parameter of interest in this case is the population proportion of right-handed toads. So we're going to call that P. And our null hypothesis is that P is equal to 0.5. So in other words, there's just as many right-handed as left-handed toads in the population. And then the alternative hypothesis is that P is not equal to 0.5. So that's our first step. We've set up our null and alternative hypotheses. Our second step is to calculate our test statistic. So looking at our experiment, we observed 14 right-handed toads. So that's our test statistic. Our third step is to calculate the p-value. So the p-value is the probability of obtaining data that shows as great or greater difference from the null hypothesis if the null hypothesis were true. Okay, so let's break that down in this context so we can understand exactly what it means. So let's think about if the null hypothesis were true. So if the null hypothesis were true and p is 0.5, then we've got just as many left-handed toads as right-handed toads in our population. And we're taking a sample of 18 toads from that population with equal numbers of left and right-handed toads. And we're asking ourselves, what is the probability of obtaining sample data showing as great or greater difference from the null hypothesis? So what does that mean? So in our sample, we got 14 right-handed toads. So that would be data that shows as great a difference from the null hypothesis. What would be a greater difference? Well, 15 right-handed toads, that would be a greater difference. Or 16, or 17, or 18. So each of those outcomes would represent a greater difference than from the null hypothesis. But we should also think about the possibility of having more left-handed toads, because that would also indicate that P is not equal to 0.5. So results that would be as great as getting 14 right-handed toads would be getting 14 left-handed toads. And a greater difference would be if we had 15 left-handed toads, or 16, or 17, or 18. Or if we frame this in terms of the number of right-handed toads, it would be either 4, or 3, or 2, or 1, or 0 right-handed toads. Okay, so those are outcomes that would show as great or greater difference from the null hypothesis. Okay, so how do we go about calculating that p-value? Because the p-value is a number that we need to be able to calculate. Okay, so let's go to R and see if we can figure out what the p-value is in this case. So we're going to run a simulation that simulates 10,000 random samples of 18 toads from a population in which we've got equal numbers of left-handed and right-handed toads. Okay, so to do that, I'm going to set up a vector that we'll use to store our results. And then I'm going to run this loop, which is going to take samples of size 18 from our population in which we've got equal numbers of left-handed and right-handed toads. Okay, so for example, I'll just show you one sample. We've got first toad right-handed, second toad left, right, left, 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 and so on. Okay, so we've got 10,000 of those. Okay, and I've stored in this results 18 vector the number of right-handed toads in each of those samples. Okay, so here's just the first few hundred. So in the first sample there were 11 right-handed toads, the second one 9, and then 13, and then 10, and then 12, and so on. Okay, so you can see we're getting different results for each sample, and so the question is, in our 10,000 samples, what does that distribution look like? So we could draw a histogram to see what it looks like. So it's a nice symmetric distribution. We've got a sample of size 18, and from our population we've got equal numbers of left and right-handed toads, so the most likely number of right-handed toads in a sample is 9, so that's the highest bar there, and then this bar is with 7, this one is with 8, 9, 10. Okay, we could count them off. Okay, so this high one is 9, 10, 11, 12, 13, 14, 15, and so on, all the way up to having 18 right-handed toads. Is there weren't many samples with all 18 being right-handed, and then we can count down as well: 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. The number with 0 right-handed toads and all of the toads being left-handed, there weren't many of those either. Okay, so this is a graphical representation of our null distribution of our test statistic in this case. And so we could tabulate that. If I turn it into a factor first, and then I'll tabulate it. Okay, and what I've done is I've calculated the relative frequency for each category. So I've got the number of right-handed toads in this column of the table going from 0 up to 18, and then this frequency is the relative frequency out of the 10,000 samples of samples where we had 0 toads. So there were 0. There were actually 0. There weren't any samples with 0 right-handed toads. There was 1 with 1 right-handed toad and 17 left-handed toads. There were 4 with 2 right-handed toads, and so on. And you can see the most common result was to get 9 right-handed toads and 9 left-handed toads. So 1,907 out of the 10,000 samples had equal numbers of right and left-handed toads, and then counting up again, we had 1 with 17 right-handed toads and 1 left-handed toads, and we didn't have any samples where all the toads in the sample were right-handed. Okay, so finally we're in a position to calculate our p-value, because remember our p-value is the probability of obtaining data that shows as great or greater difference from the null hypothesis if the null hypothesis were true. Okay, and this is a frequency distribution of the number of right-handed toads if the null hypothesis is true. And so data that shows as great or greater difference from the null hypothesis, well, we discussed that earlier. We said that 14 right-handed toads, that would be as great of a difference. 15 would be greater, and 16 and 17 and 18. But we also said that as great of a difference would be if we had 14 left-handed toads. So in other words, 4 right-handed toads. And then greater difference would be 3 right-handed toads to 1 and 0. Okay, so our p-value is going to be, if we add up these probabilities and then these probabilities and add them together, that will give us our p-value. To make the calculation a little bit easier, what the book does is it just takes these probabilities in the upper tail, adds them together, and then multiplies by 2. And so that's making the assumption that this distribution is exactly symmetric. And we can see if we actually match up the numbers, we can see that it's not quite symmetric. But for illustration, it's close enough, and it makes the calculation a little bit easier. So if I add up these probabilities, so 0.0121, 0.0026, then I get 0.0152. Okay, so that's the sum of these 5 probabilities here. And then if I multiply that by 2, okay, that's going to give me approximately what I would get if I was to add these 5 plus these 5 in the other tail. Okay, and in this case it gives me a p-value of 0.0304. Okay, so the probability of observing a result as great or greater of a difference from the null hypothesis if the null hypothesis were true is only 0.0304. Okay, so what this is telling us is that that result that we got in our experiment with 14 right-handed toads, it's, if the null hypothesis were true, we've seen something pretty unlikely, okay, with only about a 3% chance of happening. And so is that sufficient for us to reject the null hypothesis? Okay, so we've seen something that seems very unlikely, and so is this probability, this p-value that we've calculated, is that low enough that we would say, I'm going to reject that null hypothesis. I don't feel comfortable with that null hypothesis because I'm seeing something that's very unlikely to have happened if the null hypothesis were true. So to make a decision and to draw a conclusion, we need to have some threshold that we can compare this p-value to. And that threshold is known as the significance level of the test. And typically, a common value for the significance level of a test is 0.05, so 5%, 1 in 20. And so if we use that particular significance level here, our conclusion, our decision would be to say, okay, our p-value, 0.0304, is less than our significance level, 0.05. So I'm going to reject my null hypothesis in favor of the alternative hypothesis. And then my conclusion, I need to link this back to my hypotheses and my experiment and what am I trying to do. So I've rejected the null that p is equal to 0.5 in favor of the alternative that p is not equal to 0.5. So the data seems to suggest that the proportion of right-handed toads in the population is not equal to 0.5 at a 5% significance level. So that's an illustration of how hypothesis testing works. There's a few more details that we need to talk about, and so we'll spend a little bit of time talking about those details in the next video.